There was no sound of the video, so we will just start the video again. Europe is full of barriers, and many people have no clue what that means, what the impact is of these barriers. And even worse, many people have no idea where they are. So that's why we started the AMBER project. We have like 20 partners from 11 countries really looking into this issue.
And we collected all the data available, which doesn't mean it's complete. And what we're trying to do with this is facilitate to river managers the total number of barriers that we know. And this number goes up to at least 600,000 barriers. For the very first time, all this data is being collected, and we are going to create the first pan-European atlas of river barriers.
One of our partners in AMBER is Oviedo University. Using the spectacular Nalón River in Asturias region, they have been able to really incorporate a new layer in AMBER's outreach program.
Resulta que todas las especies dejan alguna traza, alguna señal en el agua a partir de la pérdida de células, a partir de los fluidos, y nosotros a partir de una sola botella de agua podemos, utilizando el ADN ambiental, tener una lista de las especies que han estado en un momento determinado en ese ambiente. Los principales resultados que hemos encontrado es que efectivamente las barreras están afectando en algunos casos la riqueza de especies que podemos encontrar luego de los embalses.
For AMBER, the social impact is also something important to keep in mind in our relationship with nature. Oviedo University in Spain is also working on that.
Hemos hecho 2000 encuestas en distintos países europeos, preguntándole a los ciudadanos qué opinión tenían sobre los embalses. Están a favor de los embalses, pero también quieren que las autoridades públicas preserven el entorno medioambiental y lo protejan y lo cuiden. Reclaman la eliminación de barreras accesorias de los ríos de Europa que interrumpen el curso de las aguas.
The case in France is completely different. EDF, the largest electricity company in France and one of the largest in the world, has understood the idea of engineering around nature when river barriers are necessary.
Le problème du barrage de Poutès, d'un point de vue environnement et pour les saumons plus particulièrement, c'est que la retenue étant assez longue, les poissons, les petits saumons, quand ils repartent vers la mer, avaient du mal à en trouver la sortie et avaient tendance à se perdre dans la retenue. Donc l'objectif du projet de reconfiguration du barrage de Poutès, le nouveau Poutès, c'est, en diminuant la hauteur du barrage de façon importante, d'arriver à réduire la longueur de retenue, ce qui permet aux poissons de dévaler plus facilement. Et ainsi, en faisant passer le barrage de 20 mètres de haut à 7 mètres de haut, la retenue passe de 3500 mètres à seulement 400 mètres de long. Donc on n'a plus du tout d'effet de la retenue sur la dévalaison des saumons. Pour la montaison des saumons, là, on va travailler avec 2 vannes centrales qui seront positionnées au milieu du barrage et qui seront totalement ouvertes 3 mois par an pour permettre aux saumons de remonter la rivière librement, sans entrave, puisque quand les vannes seront levées, la retenue disparaît complètement et il n'y a plus aucun obstacle à l'écoulement de la rivière, et donc le poisson peut transiter librement au travers de l'ouvrage. Un aménagement important, et on arrive à concilier avec ce projet la préservation de l'environnement et la production d'énergie. Alors c'est un projet qu'on a construit collectivement. Il est le fruit d'un travail entre les élus, entre les associations de protection de l'environnement, EDF et les services de l'État. Et c'est en travaillant ensemble qu'on est arrivé à trouver finalement ce projet qui est avant tout un projet de territoire.
And the greatest impact that probably AMBER has brought is the paradigm shift. AMBER is reminding people that rivers are more than fish are more than salmon, barriers are more than dams, and water abstraction is more than hydropower.
there was some wise words from our colleague Pao about rivers are more than fish. And that's what we're going to talk about also today, about fragmentation of rivers. Welcome everybody, thanks for joining us on this second session of the summer camp from AMBER project. AMBER is about adaptive management of barriers in European rivers. And in this second session, it is more like a workshop type of thing where you can ask questions, etc. We will be talking about decision support tools and prioritization of barriers in rivers. And I would like to repeat, like with the former session, people who are now joining as attendee, you are in view and listen only mode. But you can ask questions through the Q&A. You can add some links or share things if you want via the chat. And later on, if there are questions being asked, I can also introduce you to become one of the panelists. And so we have more like an interactive sessions. I am always interested about the people who will be here. I'm going to ask you a question, something more about it in a minute. Just a quick overview of the program. Today we will, as mentioned, talk about decision support tools for prioritization. And tomorrow we have 2 sessions again, and Wednesday we'll have 1 session again in the morning. This time Jess O'Henley is going to talk to us about the decision support tools, and later Simone Bizzi, also from both from the AMBER project, are going to tell us more about the sediments issue aspect. As mentioned, rivers are more than fish only. But like I mentioned before I start, I'm interested to learn a little bit more about yourselves, people watching at the moment. We have prepared a poll. Bas, can I ask you to launch the poll of who is in the audience, please? So, are you a researcher, a policymaker, a water manager from industry? People answering already. I see that most of the people have an academic background, which is around 50%. Then we have quite some people from the industry, quite some people from NGOs, some water managers, resource managers, and other. Okay, now that is very nice to know. Welcome again. And let me then start by introducing Jesse. Jesse, are you there?
I am. Thank you, Arjen. Should I start my video?
Yes, please.
It's blocking me. I think you need to unlock me.
Yeah, that's Bas. Can you
start my video?
Yeah. You should be able to do it now, I think. Yes.
Great.
And you can share your screen as soon as you want to. Jesse, it's all yours.
Lovely. Thank you very much. Hopefully everybody can see and hear me. I will start my presentation. There we go. So welcome. I'm going to talk about a few things in this short talk. I'm going to basically focus on some of the tools we've developed for AMBER for helping to prioritize the removal, replacement, or mitigation of barriers. And so I've kind of a brief outline, part 1 through 4. If I have time to get to part 4, we'll do it, but I really wanted to focus on parts 1 through 3. So I wanted to kind of give a brief background on the different prioritization methods that are potentially out there. Our particular thing is a type of optimization model, but to be able to understand kind of what an optimization model is, I want to be able to juxtapose it with the other potential options. So I'll talk about scoring and ranking, I'll talk about graph theory models, and I'll talk about informal methods as well. I'll talk about this, it's called the RIP tool, the River Infrastructure Planning Tool. So it's a nice Excel-based tool for planning the, optimize the removal of barriers in a watershed or multiple watersheds. So I'll talk about some of the data requirements, go very quickly through the user interface. It's a tool that will soon be made publicly available. So if it's of interest, certainly get back in touch with us. I'll then talk about an actual real-world case study applied to the River Wey in England, which is where I'm located. And then again, I said if I have time, I'll talk about a more advanced model that we applied to the Neckar catchment in Germany. So part one, prioritization methods. So I think we will probably all agree here that the status quo of having large numbers of barriers in place is really just not an option. It's just extremely damaging to the environment. So what is the option? Well, we need to start trying to either get rid of the barriers or at least try and mitigate their negative effects on fish, other aquatic organisms, etc. Now, the real trick though with this is how can we do this cost efficiently, okay? How can we get the biggest bang for the buck, if we will, by picking the right barriers to remove? So what are the ways of going about it? Well, okay, you can roughly break it down into informal methods, which is basically think expert judgment, or we can think about more formal methods, which is going to involve some sort of quantitative analysis. Now, the typical ones there are scoring and ranking, graph theory models, optimization models. And I would put those in increasing...
Jesse, are you showing your presentation? Because we don't see it.
I apologize, yeah. No.
Oh, yeah. I thought, oh, it's interesting. He's doing a presentation, but you are actually... yeah, all right.
Okay, snafu on my part. Okay. Okay, I'm sorry. Can we see me now? Is that better? Okay, I'm assuming that nobody's jumping in to say it's fine now. Sorry, so we didn't miss anything. We've got prioritization methods. This is just my outline, as I said. Okay, so the status quo, not an option. We need to try and figure out how to do this cost efficiently. I think we're all caught up now. Apologies on my part. So what can we do? We've got informal methods, we've got expert judgment, or we've got the formal methods, as I said, that are going to be kind of some kind of quantitative analysis. And the scoring and ranking, graph theory, optimization, they're basically, I would say, in increasing order of sophistication and preference. Okay. So what do I mean by informal methods? This is actually probably the most common thing that people do. Okay. Let's get a bunch of experts in the room. Typically, it's mostly biologists. Occasionally, it might be some engineers as well, maybe occasionally some policy people, maybe people who are focused on other social aspects to deal with maybe hydropower or water storage or whatever it is. And then they'll just basically say, get a map out and say, okay, what do we go after? And usually, if you're dealing with a small catchment and you got some good experts, it's probably not that difficult to do. You can probably figure out the first few initial set of barriers to remove. Well, that's perfectly fine. It gets a lot more complicated, though, when you scale up, though. So this is actually an example that was explained to me that how DEFRA and the Environment Agency plan it out. It's the divide and conquer filtering approach, as they said. So they basically said, each of the regions, you guys come up with your list of priorities for removing barriers. Okay. And then they applied some sort of filtering process at the national level, which was never explained to me correctly. And then they would start picking barriers. Okay. Well, I think there's a lot of drawbacks with that. And so I just wanted to, very briefly go over that. What are the drawbacks? Well, first of all, it lacks rigor. Okay. You're going to be very heavily reliant on local knowledge. So if you have very good local knowledge, great. But if you don't, I don't know exactly what to recommend to you. Big key thing is it's very, very subjective. Okay, there's no really common yardstick for saying, well, what am I trying to achieve, or what are the benefits of doing one type of removal project or repair project against each other. So you could think about a dam. I could put on a fish pass on it, or I could remove it entirely. Well, which one's better? I mean, probably typically removal, but that, what are the costs involved? What am I losing, etc. That's very difficult to sort through all of those things. What it really, I think, falls apart is when you're on large spatial scales. So if you're dealing with multiple watersheds, I don't know how you're going to figure out which barriers to remove across all the different watersheds. You're going to need a lot of local knowledge for that. And then it really still doesn't allow me to kind of compare of which, well, I've got a limited budget. How much money do I put in this watershed versus that watershed versus that watershed? It's I think, very completely unmanageable at that level. So, and it really, and as I said, it's really not getting at the problem of how to allocate funds efficiently. Given a budget of £1 million or €1 million, what should I go after? This doesn't tell me what the best thing to do is. So, formal methods, here we're going to use some sort of structured, systematic way of trying to do the decision support. And it's going to force us to have a measurable criteria of what barrier mitigation is going to do for me. Okay? So it's already forcing me to get quantitative and focus on what's important to me. And I think that's very good, because it's going to force you to have clear and objective goals. That's okay. So what are my goals? Do I want to increase habitat? Do I want to focus on patagamous fish or diagamous fish? Both? I don't know. And so it's going to force us to start sorting through all these different elements. It's also going to make us to hopefully have coordinated action. What happens if I remove this barrier downstream and this other barrier upstream? What is the net, combined impact? Okay. Hopefully, it'll be cost efficient as well. Now, that's really something I want to focus on in particular. Okay. So just so we can frame it ourselves, so we're all kind of talking from the same page, our goal is roughly, we're going to be trying to maximize the amount of accessible habitat. It could be quality weighted. It's typically measured in river kilometers, but it could be some aerial amount. It could be whatever, however you want to measure it. And we could focus on one or more species or guilds, whatever we want. That's fine. We've got some constraints though. This is what's limiting us. So I can't go and remove all the barriers across a watershed or multiple watersheds. Why not? Limited budget typically. Okay, so I've got some sort of limited budget. It's going to force me to only pick a subset of the barriers. And maybe I potentially have other requirements too. Maybe I can't lose too much hydropower by removing all the hydropower dams, and I don't want to lose maybe too much water storage capacity. Or maybe I have things about maintaining navigation along rivers, which is important, say, in the German context. So our problem statement is, which barriers should we repair, remove, aka mitigate? So I'm going to use mitigate as a generic thing, and it could be put on a fish pass. That's also mitigate. And we want to maximize net habitat gain subject to a budget or other requirements. So that's our basic goal, if you will. Again, just so we're all clear, I think people know this, but very quickly, we need to consider how passable barriers are. Okay? So we're going to use the term passability. It's going to be measured for us on a 0 to 1 scale, and it's going to measure the fraction of fish that can go upstream or downstream through a barrier. Okay? So a full barrier would be 0, has 0% passability. A structure that does not cause any impedance to fish would have passability 1, and then you can have numbers in between. So a 0.5 would be intermediately passable barrier. Okay? So I can think about these barrier passabilities on a barrier by barrier basis. Okay, but usually in a catchment, we're not dealing with one barrier. We're dealing with multiple barriers. Okay, so when we're dealing with multiple barriers, I really have to start thinking about cumulative passability. So how passable are a series of barriers? Okay, so for simplicity, and this is usually just partly mathematical, but partly because people don't have enough data, but we're going to just take the product of the individual passability values, and we're going to say that's the cumulative passability. Okay? So I always like examples because I teach at a university, and I always think examples are a lot of fun. So I've got my example here. I got my example barrier network. I got a little stream network with barriers labeled as with the letters there. So I've got A, B, C, D, E, and F. Okay? So I'm going to focus on, for the purposes here, I'm going to focus on diagamous fish that are traveling from some source up to going upstream and then traveling back downstream. Okay? And so Atlantic salmon would be a good one, or possibly say lamprey. But this could be generalized to consider patagamous fish that are kind of traveling throughout the river network. But for simplicity, we'll focus on this. So the river is going downstream, fish are trying to go upstream. And I know a bunch of information about each of these barriers. So I know its current passability. So say for barrier C, it's a 0.3 passable barrier, pretty low. To remove or replace it is going to cost me 70,000 euros. And there's a net upstream habitat of 4.3 kilometers, which would be this whole area up here. Okay? B, it's an impassable barrier. 0 passability, 120,000 euros to replace or remove. And it's got this little short 0.9 kilometer stretch up above. Okay? And I've got the same thing for all these other ones. This one, NA here, D, would be a barrier I'm not allowed to fix. Okay, it has to stay there. Maybe it's a natural barrier, or just for whatever reasons, I'm not allowed to remove or replace it. Okay? So if I want to think about cumulative passability, okay, as I said, we're just going to take the product of the passabilities. So for barrier A, its passability is 0.4. Simply, the cumulative passability, what's the likelihood fish could get above barrier A? Well, 0.4. Fine. Let's think about D. D has a passability of 0.5. So to get to above D, what would they have to do? They'll have to pass A, they'll have to pass D. So I'm going to take the product of the two passabilities, 0.4 times 0.5, which will give me 0.2. And similarly, if they want to get above F, I have to multiply the passability of F, D, and A, and it would be 0.02. So we can see here, barrier B, it's 0 passable. So nobody's going to be able to get above it. And even though C is a 0.3 passable, it doesn't matter because B downstream is 0 passable. So again, the cumulative passability to areas above C is going to be 0. Fine. So that's about as complicated as the maths is going to get in this particular presentation. So that's the good thing. Scoring and ranking. So this is one of my formal methods for doing it. So scoring and ranking, by far the most common approach if you're not going to do informal methods. So this is the most common formal method, if you will. Okay. So the main appeal of it, it's very simplistic. Okay. Pretty much anybody can implement it. You could do it in Excel. You could do it on a piece of paper. To quote a famous scientist, Hugh Possingham, somewhere right now, somebody's thinking up a scoring and ranking procedure. So fine, it's simple, but I usually like simple, but in this particular case, it's too simple because it's extremely, extremely inefficient. And I'll show that real quickly. So what's a typical scoring and ranking thing? Well, a typical scoring and ranking thing would be this, okay? It'd be kind of net benefit scores, if you will. So I'm going to take the amount of upstream habitat for a particular barrier, J. I'll multiply it by how much passability would increase if I remove or replace it, and I'll divide it by the cost. So it's a benefit cost ratio. Okay? So this is a very common way. And what I'll do is I'll then score each of the barriers, then rank them. So whichever one had the highest score gets at the top of the list, the next one's at the second, and then third, and I go all the way down. And then typically with a scoring and ranking method, you start with the barrier at the top. I'll fix that one first. Then you go to the next one, go to the next one until you run out of money. Okay? So let's look at our simple little example here. So I did that. I did my little scoring procedure I showed before, my benefit cost ratios. And it comes out that C has the highest score, followed by E, then F, then B, then A. Okay? And I've got my cost that I put up against there. So we can imagine the following. Let's say I have a 100,000 euro budget. So what would I go after first? Well, I go after C. That would leave me 30,000 after I fix it. Nothing else I can fix, unfortunately. So with 100,000, I'd go for barrier C. Okay, so with my scoring and ranking I showed here, barrier C, solution is C. And let's think about it. I fix C. Okay, so its passability now becomes 1. But what happens to the cumulative passability? It's still 0 because I have this 0 passable downstream barrier. Okay? So my net gain actually turns out to be nil. I get nothing for this. Okay, so I spent 100,000 and get nothing. Now, what you could do is actually check every possible combination if you want. And that would be the optimal thing. And I'll check and find out actually E is the best thing I should do if I only have 100,000, and I get a very small gain of 0.192 kilometers of a river. Fine, it's very small, but this is a small toy example, and you can imagine this scaling up. Okay? So instead of 0.192, maybe it's 19.2 kilometers or something. Okay? So another example, I got now 200. What would I do with scoring and ranking? I go for C because it's at the top of the list. Then I go for E, and then I now only have 30,000 left. Nothing else I can do. So my new solution would be C and E. We already saw that I get nothing from C. And from replacing E, I get 0.192. So I know actually my gain is going to be 0.192. Now, the actual optimal thing to do here now, though, would be not to go for C, then E. It would actually be to go for C and then B, which is actually near the bottom of the list. And if I did that, fix those two together. Okay, so that was the other solution. Oops, sorry. Well, okay, it's not here right now. But the optimal solution would go for B and C. So we'll replace those two, and now suddenly this whole area up here is now accessible. And I get a gain of 3.318. Now, again, it's orders of magnitude larger than that. Okay, so I know it's a small number, but it's an order of magnitude larger. So I'm getting significantly much more by going for an optimal solution, if you will, checking every possible combination. Okay, so that was a toy example. Here's a real world example I did from the state of Washington, the Pacific Northwest. We looked at the optimal solution versus what you would get with scoring and ranking for this small little watershed. I think it was near Seattle. And it looked like in some cases when you had small budgets, okay, that you're getting a large amount of habitat that you were not getting a gain out of. Okay, so this is foregone habitat. How much habitat, what percentage of habitat am I missing by going with scoring and ranking? We can see it, particularly at low budget values, it does extremely badly. And what's really critical here, though, is typically when you're dealing with barrier removal, you're dealing with small budgets. You're usually in this area. You're not usually dealing with a bunch of money to remove everything. So when you have small amount of money, it really matters what you go after. Okay? So what's wrong with it? Scoring and ranking really misses the spatial structure of barrier networks. It ignores the downstream barriers typically. Okay? Combined with that, it also does things independently. Okay, so instead of looking at how the combination of projects might change cumulative passability, what it does is it assumes I'm going to fix one barrier and all the other barriers remain static. Okay, all their passabilities don't change. But that's not actually the case, because if I'm doing multiple barriers together, the cumulative passability is changing. And so it's this interactive effect that is failing to capture. It's ignoring the interactive effects when I'm removing multiple things. Okay? So especially when you have multiplicative stuff, you're going to have interactions. Okay? So what can we do? Well, we got two options. We can go for graph theory, which is great, or we can go for optimization, which is even better. Okay? It's basically graph theory on steroids. So graph theory, real briefly, it looks at the spatial structure of barrier networks. It does consider these interactive effects of the decisions. And the way I do it is I create some sort of graph, so nodes and arcs. I'm going to show it real quickly. And then I have to develop some sort of index that measures how good a potential solution is. Okay? So a typical one, so I've got my barrier network. What I'm going to do is I'm going to convert that into a graph. It's now a graph. Okay? So I'm just considering now that the barriers are my nodes, and these arcs are showing how the barriers are connected. Okay? So I know that E and F are above D. I know that B and D are above A, and I know C is above B. Okay? And I know all of these are above A. Okay? So it'll be a graph representation of it. Okay? And again, if the math doesn't make sense, that's perfectly fine. But this is a very common one. It's called the Dendritic Connectivity Index, DCI, by Coate et al. 2008. And really, it's actually not that bad. So D stands for I'm dealing with diagamous species. Here I'm doing some sort of normalized length. How much habitat is above the barrier, just like I said. And then here, that's just actually the cumulative passability. So I'm taking the cumulative passability, multiplying it by the amount of habitat above. So I'm getting cumulative passability weighted habitat. So just like we were dealing with before. And then here it's being normalized though. So it goes on a 0 to 100 scale. Okay, so that would be the index that I'm talking about. Now with graph theory though, it does handle these interactive effects, as I said, but on the downside though, it's really only designed to do what if analysis. It's, you know, what would I get if I did this combination of barriers or if I did this other combination of barriers? And you could say, okay, plan B is better than plan A, plan C is terrible. That's fine. But what it doesn't give you is any guidance on how to come up with those plans. It's up to the user or the decision maker to come up with plan A, B, C, D, E, F, G, okay? Which can be very, very difficult if you're considering hundreds or thousands of barriers. How are you going to come up with a nice little plan, okay? And then you don't even know, is your plan any good or not? So it's nice, but it doesn't quite get us all the way where we want to be. Now, optimization does. So it's going to take a graph theoretic structure, but then it's going to go a step further by optimizing the decisions for me. It's going to effectively look for, or at least implicitly look through every possible combination of barrier removal projects, okay? If N is the number of barrier projects and I can, or number of barriers and I can remove or not remove something, it would be 2 to the power N. So it can look through that number of barriers. So if you can imagine 1,000 barriers, 2 to the power 1,000 is an astronomically large number. An optimization model will search through that entire space. What's great about it though is it gives me an objective and systematic framework for thinking about the problem. And what optimization automatically does is it gives me the most efficient use of limited resources. It will give me the optimal solution, a solution that can not be done any better by, and that's great. What it can also do, and I'm going to show this real quickly, is it can balance multiple possibly competing objectives and constraints, and that's really nice. It can even handle uncertainty, although I'm not going to deal with that here. Okay. So what does an optimization model look like? Yeah, a little bit scary, I'll admit that. But as I tell my students, you studying a foreign language, when you first see it, it doesn't make any sense. Math is the same thing, but once you study it enough, it is a foreign language and has meaning to it. So this is a real basic one. I'm not going to spend any time on it, but I want to maximize my habitat connectivity. I need to know what the cumulative passability is. That's what this line is. This next line is I can only do up to one barrier removal. Okay, so if I could have multiple projects, I could put a fish pass on a barrier, or I could remove it, or I could do nothing. Well, I can't do all three. I can only do one of those projects, and that's kind of what it's saying here. Here, simply, I got a budget. I can't go over my budget, and then I've got to, I can either do something or not do something. I can't halfway do something. So pretty basic, actually, in that sense. Okay? Now, trying to come up with these values for alpha and x that are going to be optimal values, that's really difficult, and that's where you come up with a very fancy algorithm that will kind of churn through, find the best combination of x and alpha. Okay? So real briefly, here's my summary for this, and then I'm going to do a nice little demo. Informal methods, is it objective? Not really. Does it provide for coordinated action? It does if the decision makers are thinking it in the back of their mind. Is it cost efficient? No. Okay, so definitely not. I give it a C-. Okay, that's just me. Okay, scoring and ranking, I would actually give it an F. So it's objective, I'll give you that, but it's certainly not coordinated, it's certainly not cost efficient. I think it just gives you the veneer of something that is really powerful, but it doesn't actually get there, and it's misallocating your resources. Graph theory, again, it does much better. You've got coordination automatically. I've got it's very clear objectives. It's very systematic, but it's just not cost efficient. Whereas optimization ticks all three boxes for me. Okay, so I'd give it an A, but that's me. Maybe we'd give it a B+. Okay, so part two. So that kind of puts everything in context. What I want to talk about is this particular tool we developed for AMBER. It's called the RIP tool. Okay, so what it does is it'll identify the most cost-effective mitigation projects in order to maximize accessible habitat, again, possibly quality weighted. And what it'll do, though, and what's really nice, is it'll balance multiple things. Okay? So I got my implementation cost for the projects. I've maybe got hydropower, and I've maybe got water storage. So it'll consider those three aspects. Okay? Now, how does it work? Okay, and I'm going to show it in a second here. It integrates information on barrier passability, as we said. We need to know the amount of habitat above barriers. We need to know mitigation costs. We need to know existing hydropower potential and existing water storage potential. And we need to know how those values will change if I then implement a particular project. And what's really nice is it does account for this spatial structure of barrier networks, and it will consider the interactive effects. Okay? So what's nice about it, and I think is a nice plus, it's got a very simple, friendly graphical user interface. It's in Excel. Anybody can use it. Okay? It will perform optimization runs for any given budget and any specified level of hydropower water storage. And it will do some additional what-if analysis. So you can create user-defined solutions. What if a certain set of barriers have to be repaired or a certain set of barriers can't be repaired? So I can kind of run that sort of stuff. And it'll allow me to consider multiple mitigation projects for a barrier, and it'll allow me to focus on diadromous and or patadromous fish. Okay? So one key thing, though, is it considers that the barrier network, the river network, is single-threaded. So on the left side, I can do that. That's what it's set up to do. It's not set up to do something like this, where I have barriers in parallel. Okay, so it can't do that. Okay, so here's my little RIP demo. Okay, so I've got it over here. It's right here. So I got again, this is a prototype, but it's being developed. So we got a nice little intro. What is it about? We hit next, and we've got barriers. So this is actual barrier data from the River Wey catchment in England. Okay, I've got, how many barriers have I got? I've got 677 barriers. It's in the Wey catchment, as I said. This tells me what the immediate downstream barrier is. So for barrier 1, the barrier W2 is downstream. Okay? For barrier 6, barrier W70 is downstream. If I go down here for barrier 667, there is no barrier downstream. That's NA. Okay, so I know how much the net habitat is above the barrier. I know what its current passability is, how much hydropower it has, and how much water storage. So all of these are actually 0 for water storage, but there is some hydropower in this particular catchment. Okay. So hit next, and then you just basically load your data. So you copy paste your data from whatever you want, you paste it in there, and I hit load, hit next. Then you can list out the different projects. So I've listed out some projects for each of my barriers. Some of them don't have an option for removal, but here I can replace these kinds of barriers. Those are mostly culverts. I've got remove for that particular barrier, so that's probably a dam there. And then I've got maybe put a fish pass, okay? And we can see what the costs are. So it's going to cost me 50,000 pounds. The passability afterward is only going to be 0.42 with a fish pass, whereas if I remove for that other barrier above, the passability afterwards would be 1. Okay? And I can see what will it do to my hydropower, because that could possibly reduce, okay, depending on what I do. So I load my projects, hit next, now I'm ready to go. Okay? So we can then start running some analyses. Okay? So I'm going to jump back over here real quick. So I want to look at this. So we're going to get our feet wet with trying to answer the following questions. What is the current amount of habitat available above barriers? So I'll jump back here. So I'm going to run with a budget of 0. So if I have no budget to remove anything, I'm going to get what I currently have. So I put in a budget of 0. I'm going to focus on diadromous fish. I'm not going to consider patadromous fish for this example. So I'm going to put 0 weight on patadromous, all my weight on the diadromous. I'll not consider hydropower right now, and I'm going to go and hit solve. It's thinking. And lo and behold, I'll have habitat of 26.85 river kilometers. So that's what I currently have. And then we could consider stuff of like, well, what happens if I have 250,000 pounds to remove stuff? So I hit solve. It's thinking. And lo and behold, my the amount of habitat goes up to 38.06 kilometers. It looks like my hydropower potential with that would be the same. And now I can look and see, oh, okay, look, it means I should, with 250,000, I should remove those 3 barriers. Okay, and it tells me what the hydropower is and the water storage is. Again, we can consider one more case. What happens if I have, say, 1 million, and I hit solve? Now it jumps up all the way to 93.92. So that's great for habitat. But let's look at hydropower. What has it gone from? It's gone from 1382 now down to 1163 kilowatts. Well, that's actually a bit of a drop. That's about a 16% drop. So then you could say, well, okay, I don't really want to have that much of a drop. Maybe I only want to have a 10% drop. Well, a 10% drop would correspond to about having at least 1244 kilowatts. So I'm going to include that now as a constraint. So now I'm going to say I can't go below 1244 for hydropower. Now what should I do instead? And now what the model will do is going to sort through all the different barriers it could go for, but it has the guarantee now that the budget does not go above 1 million and that I have at least 1244 kilowatts of hydropower. So it's solving. And then lo and behold, I meet that target, but now my weighted habitat, instead of being like 93 something, it's now 82 something. So I think that kind of very clearly shows you can't, you don't get everything for nothing. Okay? So, I kind of looked at, what I didn't show this one, what happens if it's 250? We did look at a budget of 1 million and it was remove those barriers. Okay? So, and then we could consider other stuff. What happens if I have to force barriers out? Okay, so what if I can't remove one of the barriers? And I didn't show this example, but with a 500,000 pound budget, you'd remove barriers 56, 622, and 636. And then you could say, well, what happens if I can't remove barrier 56? And then you could rerun the model, okay, by forcing that barrier out. You would simply put it, I'm not going to do it, but you go to barrier data, barrier projects, you go down to 56, and you'd say, look, I'm going to force it out, put -1, okay? If you put 1 on something, it would force it in. So I'm going to put -1, and then I could rerun it. I'm not going to do that here because we're running out of time. And lo and behold, instead of 38.06 kilometers, you get 37.72 kilometers. So it actually doesn't really make a big difference in this particular case if you force that barrier out. In other cases, it might. Okay? Again, you can think about, we showed this one where what happens if I don't want a 16% reduction, but I only want a 10. And basically you're gonna get you'll get more hydropower by forcing in that requirement, but you don't get quite as big of a habitat gain. Okay? So these are the kind of what if analysis we can do. Now, it looks like I didn't quite get to the Necker case study, so I'm gonna probably take I'm gonna end the presentation here, but long story short, we developed a much larger scale problem, or a much more sophisticated one that considered not just hydropower and water storage, but was also considering things like cost of water transport, so shipping. So it had to consider shipping. It also considered things like backwater effects. So what happens if I have a barrier? How much is it reducing the hydropower of barriers upstream due to backwater effects? What were the backwater effects doing to the passability? So you can make the model as complicated as you want. Okay, and then we did that as a very complicated case study for the Necker River, dealing with many more barriers, dealing with shipping locks. We had shipping cost data, fleet makeup. We had to think about water depths. We had to think about flow depths, etc. So I'll leave it here, but you can do these much more sophisticated optimization models, and it will still allow me to kind of sort through and figure out what is the best option. So,
all right. Thank you, Jess.
Apologies,
thank you very much.
A little bit over.
A little bit over, but that's fine. Sarah, I guess there are quite a few questions here.
Yes, there are, and welcome back, Polona. So we have another question from Polona. She's asking, her first question is, I was wondering how you get the cost of removal for that many barriers. Oh, Jesse, you're muted. You're muted.
Very good question, and thank you for the mute. Okay, so you will have to invariably apply some sort of kind of standardized approach for estimating this. This is only going to be on estimates. So for some things, you're going to, I think in the balance, it's not going to be bad, because you're going to slightly overestimate for some, probably slightly underestimate for others. On balance, it'll probably be okay. But the most typical way for barrier removal costs is based on height. And so you might consider it removal based on how high it is. There's a strong correlation with height and removal costs. There's also typically a correlation with potentially with the width. So basically structural characteristics of the thing, potentially where it's situated as well within a catchment as well. It might tell you how much it costs to remove. But it's going to be an estimate invariably.
We have several questions. I was just gonna mention and to just to remind participants that there are two boxes in Zoom. There is a chat box. And there is a Q&A box. So if you want to address questions, please address them in the Q&A. So we have a question from Vivian Evans asking, do you have default feasibility costing to support efficiency calculation?
Not for costings, no. So for that Riverway one, we had to go through and talk to some experts of say, what do you think it costs to remove a culvert? How much do you think it costs to install a fish pass? How much is it going to cost to remove small dams? Obviously, large dams, there's a whole bunch of other considerations, but for small dams, it's a pretty standard approach. It's usually height and maybe, relative distance to the road. So there, again, you can kind of come up with these very simple rules of thumbs for getting a baseline cost. You can then refine it afterwards if you want. But if you're dealing, again, with hundreds or thousands of barriers, that's going to be very, very difficult to do. So you're going to just have to kind of do that. But the tool itself will not provide those costings for you. It will not provide the passability for you. That's up to you as the person looking at the problem to come up with. So it's in that sense, it's very flexible.
And then now we have another question from Polona. How do you assess passability after fish pass installation? Is that expert opinion?
Yeah, so I didn't have time to cover everything, but there are several. I mean, there's usually kind of, well, at least with the current passability of barriers, there's usually three standard approaches. One, expert opinion. Two, you can kind of do some sort of rule base, given how high it is or what the head height is. And then for a given species, I would consider that roughly 30% of the fish can pass, that particular type of structure. And you can break down by structure type as well. So these rule bases. A third one would be kind of statistical based approaches, or process-based models like fish crossing software is a well-known one in the US. So you can use one of those three to estimate current passability. Again, trying to do that for a large number of barriers becomes very unmanageable very quickly. So mostly it's down to expert opinion in practice.
So this question was about the fish passability, but then a similar question also from Polona. For water retention capacity, do you need a hydrology study to determine that?
Yeah, okay, so this is up to you as a user. If you can make it as sophisticated as you want, you can get in hydrologists, you can get in a whole bunch of people, and that's perfectly fine. It runs the gamut in terms of how sophisticated you want to come up with these estimates. So ideally, you should have hydrologists, you should have economists, you should have fish biologists, you should have everybody in there kind of putting their 2 cents in to try and figure out what is the most realistic set of data. Sometimes that's not possible, and so again, you're just going to have to make a best estimate and then move forward from there. And then I know some people kind of object, oh well, the data is wrong. Well, yeah, fine, the data might be wrong, but you still have a decision that you need to make at the end of the day. So I think not having the perfect data doesn't give you an excuse of not making decisions. So you're still going to have to make decisions, and you'll just have to do the best you can with the data you have at the time, and that's life. So I mean, that's just my personal view.
Arjen, are you still okay with more questions?
Yeah, we still have a few more minutes.
Okay.
It seems, so, I mean, I'm just an observation. It seems it might be really, really interesting to get more studies on these estimates, don't you think? Because there's quite a few questions, and I guess this can be a good priority, maybe for
yeah, no, I agree. I mean, there are initiatives. I don't know one so much in in Europe or the UK, unfortunately. I do know in the US that American Rivers is a large institute dealing with river restoration. They've actually been collecting for a number of years dam removal costs. So I've actually been able to access some of that data. So I've actually looked at the data, and lo and behold, there is a wide variability of how much a dam costs. But I've done some statistical analysis, and you can get a clear trend as the taller it gets, the more costly it is. Certain states cost more because it costs more to remove barriers in California than it does in Maine. So you can start getting kind of some of these elements. So if people wanted to kind of like, I think this would be an extension of AMBER, we could start collecting, dam removal information. It sounds like we can start coming up with that and then applying more refined estimates for this dam removal stuff.
We need, okay, sorry,
Sorry, there are a couple of questions from Paulo Branco, and he's asking if it is possible to have several solutions for each barrier. So removal, fish Y, and also can you factor in habitat quality for more than one species?
You can. This model is somewhat simple. There's another set of There's another tool I've developed in a previous life called OptiPass, which will really consider multiple types of fish. So you can go up to like 20 different species of fish. So you can do that. This one is a little bit limited to like a prototypical diagamous fish and a prototypical potadromous fish. So for the RIP tool, it's one diagamous, and up to one potadromous. But you can easily incorporate quality. So if you have some sort of quality score, I would normalize it on, say, a 0 to 1 scale. 0 being not suitable, 1 perfectly suitable. You just simply multiply that number by the amount of habitat, and now you have a quality weighted habitat score. So there's nothing wrong with that. Coming up with those 0 to 1 scores is very common in the habitat suitability analysis type of literature. They do a lot of that with taking presence absence models and then some environmental factors and trying to figure out how suitable a particular area is for a species. So you could easily apply that as a pre-processing step and then adjust the habitat values by that.
And how can you get assessment of current fish passing the barrier factor?
Yeah, it's again, you're gonna have to come up with estimates. You do need as a minimum to know where the barriers are. Again, as a minimum, it would be good to know what kind of barrier it is. Is it a dam or is it a culvert? And then if you have additional structural information, that's where you can kind of apply these rule bases. So if the dam is, say, maybe over 3 foot, or 1 meter head height, maybe it's impassable for all fish except for salmon. Okay, and then if it's over 3 meters, then it's impassable to everybody. And then if it's a culvert, maybe it's okay as long as the the angle of tilt or the flow flowing through it is not too high, or if there's not a if it's not a perched culvert. So you would need to have some sort of structural information, but that's usually what you would do anyways when you're surveying a catchment. You figure out where are all the barriers, and you do a quick assessment to say, a few basic structural pieces of information. Then you can use that structural information to estimate the passability using these rule bases. And if people are really interested, I can certainly share these kind of rule bases that people have developed for the UK or the US or other places. And then you would adapt.
Slovenia, for example, I see.
Yeah, exactly. For Slovenia, you could take one of these ones and adapt it for the Slovenian case. So because the UK one's not going to be perfect, but you slightly modify what it is.
And there's also somebody asking, Jesse, if you can share the Occupass or something you said.
Oh, OptiPass. Yeah. Okay. So OptiPass, that is currently available. If you want to get it, contact me directly. It's free for non-commercial uses though. So if you're planning to use it for commercial uses, you would need a commercial license. But
maybe you can share a link otherwise on the chat.
Yeah, unfortunately, I don't have a link yet because the website I'm using went down. But if you contact me, I can share the information with people.
Okay, thanks.
One minor point is OptiPass is only for diadromous fish. Okay, so if you're thinking you want to do patadromous fish, OptiPass will not currently work as is, but there are potentially development plans to extend it as well.
Okay, I think, Sarah, that we've had the most now, right? Anyway, we have to move on.
Yes.
So thanks a lot, Jesse.
Thank you.
Really interesting. Would be great to do it for all of Europe, but I guess that would need a lot of information as well.
You could try. You could try. The OptiPass tool would be certainly capable of doing it. I've done it for the entire. Yeah, I've done it with 50,000 barriers, and it runs in a matter of seconds. So
that sounds promising. All right. Okay. Thank you very much. Then we go on with sediments. We talked about fish, but it's also about sediments. Flowing rivers are important for sediments. Households of rivers, so to say. Simone, can you show us what you can tell us about what lessons learned of the past 4 years?
Thank you. Good afternoon. Thank you, Arjan. And so my presentation, as Arjan anticipated, will be more about sediment. I'm going to share the screen. Okay, you should be able to see. So in my main line of research is mostly about fluvial geomorphology, and we have been working in the last year about network scale sediment connectivity model. Basically, our aim was to understand how sediments are linked through a catchment and how anthropic structure from any kind of river barrier can obstruct and interact with this sediment dynamic, and how this is going to affect a number of fluvial processes, from fish habitat to many other kind of process, from infrastructure stability to nutrient supply and so on. So the first slide is just to acknowledge that this is the work of few people, but not only me, obviously. And I was based for most of the AMBER project at Polytechnic of Milan. This is why it's written Polytechnic of Milan, also in the program today, but I recently moved to the University of Padova. And then we have been collaborating on this topic with other people across Europe and also in US. So let's just give let's introduce the topic of sediment connectivity. So the first idea, as you probably know, river systems are deeply interconnected, and from a very general and simple perspective, we can see a riverscape, like in the mountain, you have mostly production of sediment. In the middle part, you have mostly transport of this sediment, and then is deposited mostly towards the end and in the delta. Actually, the reality, someone described this process as a kind of conveyor belt. But actually, the reality of things is much more complicated, and basically rivers are an interconnected system of sink and deposition, sink and erosion site across the entire catchment. And understanding how this sink and erosion area are linked is very important to understand how river barrier, for instance, will interact with the functionality of the system. Obviously, these are some of the main type of alteration that interact with sediment connectivity. So if we are channelizing a river, obviously this is completely change the hydraulic of the river system, and then also his ability to transport sediment upstream and downstream. One of other kind of very strong alteration in terms of sediment connectivity is riverbed mining. This has been pretty popular in Europe, especially in the second half of the 20th century. Now it's pretty popular in most, let's say, for instance, in Middle East and in Asian country where there is a big development of dams. So very often in countries where there is a developing economy, they are building big dams for hydroelectric production, and at the same time are extracting a lot of gravels along the river for building and for construction material. And obviously the mix of these two are going to have a very big impact on how the river works and all the ecosystem services present along the river. The main idea behind our work was that we were interested not to understand how a single dam affects the system in the surrounding on the dams, but how, because the system is all connected, how the cumulative impact present in a catchment are going to interact each other and are going to affect the sediment connectivity and then also habitat quality and ecosystem provided by the river. And for this reason, we try to model the system at the network scale, and we want to try to include a number of main features that affect sediment connectivity. And obviously, one of these most important features are barrier, dams, but also smaller barrier present along the river system. And very often, if we are not speaking about major dam, the most of the effect are not the single effect of a single dam, but is the cumulative effect of many dams in the entire system that should be carefully assessed, and then using this information to have a strategic planning, or for instance, where you should build dams and how you should operate them. And I'm going to show you some example in this respect. So we have developed this model that is called Cascade, and then we have also used this model in some example within the AMBER project. I'm going to show you one example. The idea is that it wants to provide disaggregated information on sediment flux and composition. It has been thought to be applied and to be designed also in contexts where you have limited data and can take into account sediment connectivity alteration due to different anthropic pressure. And then the idea is to use this model and the output of this model in a multi-objective decision framework. I will show you some examples focusing on sediment connectivity, but the output of this model can be perfectly, for instance, integrated in a framework like GES show you in the previous presentation, and then link to the information on fish habitat, also information on sediment connectivity and habitat quality. We have already quite a number of publications out about this model, and we have also a toolbox that can be downloaded, and you can find all the information on this website, cascademodel.org. I want just to give you a quick overview of how it works. Basically, you extract your river network that you want to model, then you segmented it in reach that are geomorphologically homogeneous. That means reach where you can infer that sediment transport and then associated river pattern can be considered homogeneous. Then you can add external source described in terms of sediment supply, so you can include information on dams, or also presence of bluff, ravine, information on deforestation, and so input of strong sediment input in a specific part of the river network. And then the model routes the available river sediment through the network and take into account of all the interconnection of these different cascades, because each input of sediment is a cascade that is routed through the system. And from here, there is the name cascade. And so we are able to take into account how these cascades interact each other and how they compose the cumulative sediment flux in each reach of the network. So in each reach, we can have information on kilogram per second of how much sediment is passing by in any reach of the network, but we can have also information on grain size distribution and also of provenance, so where this sediment is coming from. This is a kind of example of what information is used as input, and you have basically we need a DM, more detailed and better it is, because you extract the river network and most importantly channel slope that is used in the sediment transport formula. Then you can get information on active channel width from Google Earth imagery. Very often they are enough. More complicated is to have information on water discharge and hydrograph that normally comes from spatially distributed hydrological model. Then depending on the scale of your application, some global model exists. So it depends on the scale of your case study. You can use even global hydrological model, or you need more detailed information. And this is an example that obviously first you set the system without alteration, and then you start to include all specific input that can be natural, like an alluvial fan, or can be anthropic, like dams and barriers. Now let's go to see an example to understand, let's say, more in concrete how this works and how this can be applied in sediment management issue. So here, this example is not coming from AMBER, it's coming from a previous example. And here you have the Trieste Basin, that is a major tributary of the Mekong, and it's Mekong Delta. So what you see here in this picture, in the right of the slide, it's the entire Mekong River Basin. Here you have the river delta, the Mekong Delta. It's obviously the house of more than 22 million of people. Sediment creates the sustainability of the delta itself. So if we stop all the sediment getting to the delta, you will see in 20, 50, 100 years, the delta sinking. Also because this is happening together with other threats like sea level rising by climate change, water pumping that create land subsidence. And so it's obviously it's a complex situation where the sediment supply from upstream is even more important in this very under pressure and treated ecosystem like the Mekong Delta. And the 3S is where they are planning to build many dams. This rectangle that you see here are the dams that have been already built and the dams that will be built in the next 50 years. In this context, you don't have a lot of data on sediment, and our idea was we want to have an assessment on sediment transport and sediment connectivity of this system to understand if we build all the dams that are planned, how much sediment will stop to get to the delta, and how this can be a threat to the delta. As you will see, so let's go first to an example of how we validate, so how we can have information on sediment connectivity. So in this context, as I said, is a kind of data poor context, and we had information only at the basin outlet. So if you look here on the right, about grain size distribution and amount of sediment per year estimated from previous work here at the outlet of the basin. So each of the dots that you see here is a reach of the system. The scale, to have an idea, these are 70 kilometers, so it's a large scale exercise. And the color is how much sediment is supplied from each of these reach. And since Cascade has been designed to run pretty quickly, because we want to carry out some sensibility analysis, since we don't know how much sediment is supplied from each of these sources, we had a Monte Carlo simulation with a wide range of alternatives for each of these sources that, based on expert opinion, are considered more or less realistic. And this is to give you an idea. If you look at this graph on the left, these gray points are all the simulation, and in this plane, where here you have amount of sediment per year, kilogram per year, and here you have the grain size, D50, so the average grain size dimension. And what you see, this is information at the basin outlet, where we have field data. And so the red cross here indicate that only less than 2% of all our simulation create at the outlet grain size distribution and the amount of sediment that match the observation in the field. And this is a way to have a validation that is pretty strong in terms of amount of sediment that will reach the outlet. Probably you have a high uncertainty in each of these dots, but you are pretty robust in assessing how many sediment will get to the outlet and then to the Mekong River Delta. And then how we have used this information. We have looked at a Pareto front, so a trade-off between two, in this context, very important objective. On one side, we have hydropower generation that you see on the x-axis. It's easier if you look in terms of percentage. So you go from 0 to 100% is how much is planned from today to the next 20 years. So how much the government in Vietnam planned for the next 50 years. Whereas here is sand flux on the y-axis to the Mekong Delta, that, as I said, is a key resource for the survival of, for the existence of the delta itself. Also in this case, to look at this graph, it's easier if you look at the trapping rate. So 0 means is a natural sediment supply, 100% all the sediment is trapped by dams and will not get to the Mekong Delta. What you see in each of these points, the square and the dot point, are a different combination of dams that you see here. So each of these points is a combination of the dams, all the dams that are planned. So we play switching on and off this dam. And the rectangle, you see the trajectory of what is happening until today. Nowadays we are here, so we are building these LSS2 dams, and so we are trapping 90% of the sediment because this LSS2 dam is here, just very close to the outlet, producing around 50% of the capacity that is planned for the next decades. And we said, okay, but if we live in an ideal world and we can switch on and off all these dams that are existing or are planned, could have done better? And the answer is yes. So these circles are basically ideal solution, where this is an example where we can produce the same amount we produce today, stopping only 20% of the sediment. So the margin of improvement is in theory huge. And also, I put your attention on this nick point here. It means that the trade-off until producing 70% of the energy is worth it, because the increase in energy and the trapping rate is not too in conflict. And from this point on, it means that you kind of reach a system capacity in terms of how many dams you can install in the system. And so probably after the 70%, you should look at alternative form of hydropower production. Now I want to go quickly to the second case study I wanted to show you today. This is part of also an AMBER exercise and is in the Vjosa River. Vjosa is in the Balkan, and as many rivers in the Balkan, the Vjosa is an astonishing braided system, almost undammed, is one of the last almost free-flowing river in Europe, and is threatened by, has many Balkan river by many hydropower projects. So here you have a really valuable ecosystem that you should conserve and protect as a European. At the same time, you have a country that is developing and wants to produce more energy. So being able to understand this trade-off is really important for this case study. Again, here we have applied Cascade. Again, here is an example where we don't have field data on sediment connectivity, only few. And this is an example how, in a very cost-effective way, we went to the field in a couple of days. We take some picture and get information on superficial grain size distribution, just with some picture and some software information. And so we know the average grain size and the grain size distribution in different reach across the system. And then we have, I don't go now in detail, but we are writing the paper in this moment about this case study. We went and we had some hypotheses on the supply from all the upstream part of this system. We routed the sediment through the system, and we got information of how much sediment is transported per year all through this system. And I can tell you that this amount, especially at the outlet, and this is a range because, as always, we work in a Monte Carlo context. So we always, because with the sediment connectivity, with sediment transport assessment, there is a huge uncertainty structurally due to the complexity of the process we are analyzing. We are always working with sensitivity analysis. And this box plot here at the outlet match really, really well previous assessment in the literature that only look at the sediment and the outlet. Instead, here for the first time, we have an assessment of sediment transport distributed through all the system. So I have the last 5 minutes where I want to show you, then we validated, so the system also obviously model grain size distribution. What you see here in green are the grain size distribution, the green line at the different location that we observed through the picture in the field, whereas the red line are the Monte Carlo simulation, that a few 2,300 Monte Carlo simulation. And as you can see, they match very well. You have a pattern of finding from upstream to downstream that was expected, but more importantly, you match the grain size distribution that we observe in the field. But then here, and this is the last point I want to make, we went further. So as you see for the Vietnam, we only calculate the amount of sediment to the delta, so at the outlet, because in that case, the most important objective was to guarantee the amount of sediment to the delta. But in this case, the most important objective is to protect the river habitat that are present in this valuable ecosystem, in particular braided reach. Braided reach, to have an idea, are these very astonishing braided reach that are all across the system, but especially in this last part. And they are really hotspot of biodiversity. And it's well known in literature that when you stop sediment, so you have condition of sediment starvation, what's happening is you trigger a series of channel process that inside the system simplify the system. So from a multi-channel system, you get a single channel system in size and disconnected from the floodplain, with all kind of problems, from bank instability, habitat, loss of habitat, loss of hydrological connection with the floodplain, and all kind of water table decreasing because you have riverbed incision and so on. So we have applied, since we have information on sediment transport distributed across the system, there are formula from the literature that are able to understand when what you see in this picture here, basically to simplify it, if you have information on grain size distribution, channel parameter, channel section, and sediment transported by that river, you are able to say if that river will adjust as a multi-channel braided system or as a single channel. And this is the threshold that you see here that divide this system very well. So the blue dot point are multi-channel in this moment in this system, and the red point, the red diamonds, are single channel in this system. And we have played saying, okay, but then if I have a sediment reduction because I'm building dams, so far we didn't placing exactly the dams where they are planned, because this is something we would like to do in the future, but we have played simply saying, okay, let's say we reduce sediment of 10%, 30%, 60%, or 90% across the system. And what you see are that with 10%, most of the multi-channel braided system are these green reaches across the system will be still in place, whereas they decrease for 30%, they almost disappear for 60%, and they completely disappear for 90%. So this is a way to study the resilience of the channel form, but then of the habitat, also for fish, for instance, at the network scale. So I think I have the last minute, and so I wanted to highlight some of our progress in terms of modeling sediment connectivity at the network scale, showing how this is possible even in situations where you have data scarce situation. And especially I want to highlight, like nowadays, especially with remote sensing technique using drone together with satellite, this is what we are doing now in some case study in Italy. Is it possible really to gather very valuable information for an in-depth validation of this network scale sediment connectivity model in a very cost-effective way? And then when you have a model with a strong validation, you are able to understand really deep how sediment connectivity works you can play very well how our anthropic pressure and different sediment management strategy will impact system functionality. And this is, I have shown you two I've shown you two examples where we have played with dams, and how dams can be placed. But in future, you can play also how dams will be operated. So for instance, if you build dams that allow sediment pass by with different type of infrastructure, you can play how different hydrological operation and sediment management operation can play a significant role in restoring sediment connectivity. Okay, I think that's it.
Thanks.
Thank you for attention.
Thank you, Simone. So that is, I think, for some people also quite a new world, actually. Is that something, I was wondering, Simone, does it get a lot of attention at the moment, the sedimentation issue, when it gets to river connectivity?
Yes, actually, it depends. In some community, so if you look at the water resource community, fluvial geomorphologists, of course, but in terms of management, mostly in the water resource community and river manager community, yes, a lot. It's more a focus on place where you are building big dams, because obviously big dams are really creating an important disconnection, especially where you are building many of them, like is the Mekong case study, but Amazon is another case study where this is happening, and so on. In Europe, this is a bit less of an hot topic, wrongly in my opinion, but of course I'm biased by what I'm doing, because dams are in place since 50 years. So you have already a kind of equilibrium with the system. And so the attention is more on fish connectivity, for instance. But as always, as I say, if you don't understand how sediment moves, you cannot understand if the habitat is sustained properly, and then also the fish can live in that place. Yeah. So for me, any kind of fish habitat assessment is a bit useless is before there is not a proper understanding of sediment connectivity. Yeah. You need both, because if you do in an unstable system and a fish habitat assessment in the condition that you see today, but in 10 years, habitat will be completely transformed by natural channel process, your assessment, it's a bit useless. So you need both worlds to speak together. I have to say that in most of the big projects I know in Europe, this is happening. It's not that it's not
But
happening.
For the Vjosa, for example, your example, is that being, I mean, who is looking at that in the region there? Are they using it?
For instance, in the Balkan, yes, there is a lot of attention on sediment.
Oh, okay.
Because this system, the Vjosa and the braided system there, it's sustained by the huge amount of sediment that is carried by this river system. And they all know if they build dam, is not only a problem that fish cannot get to the mountain, here you even don't have salmon, but is that you destroy this habitat, not only for fish, but for birds and for all kinds of biotic elements.
Yeah. Interesting. Sarah, questions? Do we have questions?
We have just one new question here. So would you say sediment connectivity is crucial in all barrier sizes, or is there a limit, like maybe 1 meter, below which sediment is not considerably affected and its analysis would not be cost effective? This is from Polona.
No, this is a very good question. So let's say for sediment, most of the impact comes from medium barrier on. So even more than 1 meter, can be even from 2, 5 meter and higher barrier. So smaller barrier, normally they do not affect sediment connectivity. Actually, they do not affect, let's say, the transport of sediment downstream, but they do affect channel dynamics. If you think about an example that can be, many of you can know is in Switzerland. Rivers are very well managed, but are very rich in infrastructure. So you have an infrastructure every 500 meters very often. So they are heavily managed. This infrastructure design the river system. So the river system is stable and it deeply affects channel dynamics. So even small barrier, especially frequent small barrier, affect channel dynamic, and then also how much sediment can be entrained on those reaches and then routed downstream. So I would say even small barrier, it depends on the scale of your study and what is the objective of your assessment.
Yeah.
At the moment, we have no more questions.
Okay, now, thank you very much. Then I think we can already go to the end of this session, unless there are some more questions more in general about today's session. If not, then we continue. We will be back to you tomorrow. Let me just share the program for tomorrow. Tomorrow morning at 10 o'clock, we will be talking about wrapper berry assessment for fish habitat. That will be 2 Polish colleagues from AMBER who will talk more about that. And so we hope to see you there again. And for now, I would say I would ask Cesar if you are still there. Cesar, can you come in and you know, make a nice campfire song for us? Then we can leave, and you know, we can also let the information of this session get into us nicely. Cesar, do you hear us? No, I don't think so. He doesn't seem to be there. Then, Bas, I suggest that we do it else and we take a song from Eurovision. Bas, can we find one so we can finish our session properly? Yes, there we go. And oh yeah, this is one of my personal favorites from Owen in India. So thank you very much. This was it for today. I hope to see you tomorrow. And let's start with this song from Owen from our Eurovision Song Festival. It's still possible to vote if you want.